talk to your neighbor. What do you say? Correct answer is E. Why E? Why is it 4 times? Mathematically, why? Mathematically, what makes it 4? Squared. So when we double the speed, we still square that doubling. So we end up with 4 times speed squared. Good with that? Okay. You get 4 times the kinetic energy. So thumbs up when you have a guess. Talk to your neighbor. Correct answer is 4 times. Okay. Hopefully your lab showed this. I was hoping that was okay. Now, if it didn't, there was a significant amount of air in your lab. We were like, I said, try to get it as close to twice the speed as possible. Did anybody just nail it on twice the speed? Most that I saw were like, yeah, it's close. Right? So hopefully it was around this. If it wasn't, my guess is your initial speeds were really slow. Your initial distance is pretty small. If you have a smaller initial stuff, then any variance of that, any deviance off of that is going to make big errors. Does that make sense? You start with small measurements and then any error beyond that is going to be accentuated. Okay, so in this case, what force or forces is doing work? We got friction. Anything else? Is it doing positive or negative work? Negative work. Okay, so we have negative work equals a change in kinetic energy. At the end, you stopped. Okay, so this is equal to your initial kinetic energy. This is specific for this example. This is not something you're going to memorize. This is for this scenario. Okay, Does friction change as you go slower? Is the force of friction dependent on speed? How fast it's going? How fast it's sliding? And you guys look so excited to be here. Man, it just warms my heart. All right. Friction's still the same regardless. So you double the speed, you quadruple the amount of kinetic energy, you're going to quadruple the force, the distance that takes you to stop. 4 times the distance. Why is this relevant? Well, you all drive. So one year, it actually ended up snowing. Check. 10 miles an hour. So this is outside the cafeteria windows. So I'm going 10 miles an hour. This is me 15 years ago. Crazy. I had hair. $20 miles an hour. Okay. So I'm going twice the speed. It was like 5 feet. Five feet compared to, it looks about like 20 feet. Did you have a wig on? Did you ever have hair in your life? Yeah, I came out of the womb bald. I just never had hair. It's a rough childhood. All right. So, if you're going twice the speed, folks, that takes 4 times the distance. Not twice, as most people believe. 4 times. That is substantial. And it becomes even more apparent when weather conditions are bad. Road conditions are bad. Please take this to heart. As we were driving, we were beginning the winter season early this year. Okay, it's 30 miles an hour. In normal conditions, takes 12 meters to stop. Okay, going 30 miles an hour. Snow, 30 meters, almost 3 times the distance. In ice, 5 times the distance to stop. That's going 30 miles an hour. When's the last time you drove 30 miles an hour on a road? In your parking lot. That's the last time. Okay? I was hoping to find one that, this is the best I could find. This is 50 miles an hour. So we haven't doubled it. We're just going from 30 to 50. Okay? Your normal cruising speed through your neighborhood. Okay? Normal takes 50 meters to stop, half a football field. And this is aggressive stopping. This is not like, oh, this is like, 50 meters. Snow. Oh, shoot. 150 meters. Ice, 400 meters. Folks, that is a quarter of a mile. you're not going to stop. Whatever you see that was like, oh no, like you're going to hit it. Slow down if the road conditions are bad. It is not worth it is worth it to be late to school. Okay? Does that make sense? Like it's worth your life is more important to that. I would venture to say probably your insurance premiums are worth more than that. Just get up earlier or don't go stupid stuff. Like, okay? Does this make sense? Okay? Please take this to heart. This is like, I don't know how more applicable you can get to your life. Okay? All right. Lesson 2. By the by the end of this lesson, you'll be able to describe when something has gravitational potential energy and when it does not, determine how much mechanical energy something has, determine if mechanical energy is conserved, how to calculate different measurements when mechanical energy is conserved and when it's not, and how to create energy bar graphs. Sounds riveting. Can't wait. We're not going to hit all this today, but we will start. So, in the video pre-quiz, you got this equation, potential energy, gravitational potential energy, MGH. I just want you to know you don't have to recreate this. I'm just kind of showing you, hey, here's this where it just didn't magically appear. So gravitational potential energy is the potential for gravity to do work. Okay, if I have some object in an elevated position, gravity has the potential to do work. Okay, as this falls, gravity is doing work. It has the potential to do work at this elevated position. You good with that? Okay, now check out where this equation comes from. What's that? Force of gravity. What's this? Vertical distance, height. Force times distance. It's the work done by gravity, or the potential for work to be done by gravity if it moves that distance. Does that make sense? You're not going to have to recreate that. I'm just trying to give you an idea, help you understand what potential energy is. Okay? All right. Correct answer is D. Any of these could be true. Okay? That's not very comforting. Okay, here's the deal. It totally depends on where you define ground zero to be. Where is H equals 0? Okay? And how do you determine that? You make the lowest point that you care about, make that ground zero. Okay? If this book is doing this, the lowest point that you care about is the tabletop. Make the tabletop ground zero. Does that make sense? If the book does this, the lowest point that you care about is the floor. Make the floor ground zero. If there happens to be an earthquake and the floor is ripped open and the book falls all the way to the grass, because we're on a second story, well, make the grass ground zero. Whatever your scenario is, what is the lowest point that you care about, make that ground zero. So your value of potential energy can change depending on where you make ground zero. So you can make it anywhere you want to. However, there are places where it's smarter to make it than other places, depending on your scenario, depending on the problem. Okay? Good with that? All right. Okay, quick refresher from the video. Mechanical energy is the sum of mechanical energy plus potential energy. Mechanical energy is conserved if only non-conservative if there's no non-conservative forces doing work. Mechanical energy is conserved if there's no non-conservative forces doing work on the object. Have a conversation. Okay. Thumbs up, thumbs down. Yes, it is conserved. No, it's not. Okay. What forces are acting on the sledder? Gravity. We are on or near the surface of the earth. What else? We've got normal force, perpendicular to the surface. We're ignoring friction. Are there any other forces? He's not doing that, so there's no applied force. That's just inertia wanting to keep on going. Okay, good with that? So here's your free body diagram. The condition is if there's no non-conservative forces doing work on the object. Is gravity a conservative or non-conservative force? Conservative. It's the only force that is a conservative force that we're going to study. Okay? Is gravity doing work? Yes, it is doing work. But that's not going to change the mechanical energy. Okay? Is normal force a conservative or non-conservative force? Non-conservative force. Uh-oh. So we have a non-conservative force acting on the object. But the condition is if there's no non-conservative forces doing work. Is normal force doing work? Tell your neighbor why or why not. Is normal force doing work? Is normal force doing work? No. Why not? There's no component of force that is acting parallel to the direction of motion. It is acting perpendicular to the direction of motion. It's moving this way. Good with that? Okay. So normal force is not doing work. So is mechanical energy conserved? The condition is if there's no non-conservative forces doing work, mechanical energy is conserved. Is mechanical energy conserved for this process? Yes. Okay. Good with that? So it's not if there's no non-conservative forces acting on it. It's if there's no non-conservative forces doing work on the object. Good with that? Okay. So how does that? I don't. Okay, super. It's conserved, but who cares? How does that play out? Okay, so kinetic energy is 1/2 mass times speed squared, correct? Gravitational potential energy is mass times 9.8 times the height. As the sledder goes up the hill, what happens to the height? Increases or decreases? Increases. So what happens to the gravitational potential energy? Increases or decreases? Increases. Was potential energy conserved? Was potential energy conserved? Did this stay the same as the kid went up the hill? No. Okay. This was not conserved. What happened to the speed as the kid went up the hill? Decreased. Therefore, what happens to kinetic energy? It decreases. Was kinetic energy conserved? No. But the increase of this equals the decrease of this, which causes this quantity to stay the same. Does that make sense? How that played out? Okay. Give this one a shot. Thumbs up when you have a guess. Have a conversation. Tell them why or why not. Okay, what do you say? Thumbs up, thumbs down, yes, no, conserved. What forces are acting on it? Gravity. Normal. An applied force. Is gravity conservative or non-conservative force? Conservative. We're good with that. Normal force. Is that conservative or non-conservative force? Non-conservative force. Uh-oh. But is it doing work? No. It's acting perpendicular to the way the car is moving. Applied force. Is that doing positive or negative work? Sorry. Is it conservative or non-conservative? It's a non-conservative force. Is it doing work? Yes. Uh-oh. So, mechanical energy is conserved if there's no non-conservative forces doing work. This is a non-conservative force doing work, not conserved. Okay? Is this applied force doing positive or negative work? Negative work. Therefore, what do you think happens to mechanical energy? Are we increasing it or decreasing the total mechanical energy? If a non-conservative force is doing work, it's changing the mechanical energy. It's not conserved. It's changing it somehow. But by how much? This is the beauty of work. It is equal to how much energy changes by. So the work done by this non-conservative force is equal to your change in mechanical energy. So applied force is doing negative work. Therefore, you have a negative change in mechanical energy. Meaning that, is it gained or lost? Lost. We're decreasing. We have a negative change in mechanical energy. Now, real quick, this is different. This is a different equation than this. This is the network. This is the first time that we've made a distinction between conservative forces and non-conservative forces. Up until this point, up until yesterday, there was no comprehension of conservative and non-conservative. It's just force. Okay? This takes into account everything. Conservative, non-conservative, doesn't matter. Just all the forces. Equals the change in kinetic energy. This is big picture. This is a little more specific. This is the work done just by the non-conservative forces is equal to the change in mechanical energy. Okay? Now, this question has a tendency to throw people because you're moving at a constant velocity. I have tried to beat this into you. Constant velocity. Oh, Ooh, that's a thing. That's important because what's the consequence? What do we know is true if the velocity is constant? The sum of the forces are equal to zero. Acceleration is equal to zero. Inertia is happy. It's doing what it wants to do. Okay? But this is not the condition for mechanical energy to be conserved. It is something completely different. Just because it's moving at a constant velocity does not mean mechanical energy is conserved. You okay with that? Like we're taking a different perspective on these physical situations. Okay. So in this scenario, what's happening in potential energy? We're increasing or decreasing as the car rolls down the hill. Decreasing. As the car rolls down the hill at a constant velocity, what happens to kinetic energy? Stays the same. So we've got something that stays the same plus something that is decreasing. So what happens to mechanical energy? Decreases. Huh, that's funny. That's because there's a negative work being done by applied force, causing a negative change in mechanical energy. See how all that ties together? Big picture? Okay. All right. I hit this yesterday on the video. Okay. So if mechanical energy is not conserved, it changes. You okay with that statement? If it's not conserved, then it's going to change. Changing anything is final minus initial. I've found that negative signs are problematic. So I want to make this without negative signs. So what I'm going to do is I'm going to bring this over here. So I have initial mechanical plus the change in mechanical is equal to the final mechanical energy. I just brought it over. Okay. Now, mechanical energy is equal to the sum of kinetic plus potential. Okay, good with that? Mechanical energy initial, we can unpack that. And we can unpack this. Oops. Good with that? This is this is a popular way to start a problem. This is going to be our original equation right here. Okay. Sometimes it's helpful, rather than looking at how much energy changed by, is to look at the work done. The work done by a non-exerted force is equal to the change in mechanical energy. So we can we can swap these out. Okay. So we can say initial kinetic energy plus initial potential energy plus the work done by your non-conservative force is equal to kinetic Final kinetic plus final potential and final potential energy. Okay. One of these two, like, these are saying the same thing, just one's in terms of energy, one's in terms of work. This is our original equation that we're going to start with a lot of things that I'll show you tomorrow. Okay. Good with that? All right. This animation is pretty archaic, but it's pretty educational. Okay. This bar graph is showing kinetic energy. This is showing potential energy. This is showing work done by non-conservative force. And this is showing mechanical energy, total mechanical energy. Okay. Initially, the skier is going down an icy embankment, no friction. And then they go through some fluffy snow, and there's friction there. Okay. So initially, you've got gravity and normal force. Gravity, conservative force, we're good. Normal force, ooh, non-conservative force, but no work is being done. So during the hill part, mechanical energy is conserved. Total mechanical energy stays the same. As they go down the hill, their gravitational potential energy drops, but their kinetic energy increases because they're speeding up. The amount that this, ignore this part for right now, the amount that, oh, boo hiss. The amount that this drops is equal to the amount that this gains. So the total amount of mechanical energy stays conserved, stays the same. Okay? But once they reach the flats, gravity and normal force are doing no work. They're perpendicular direction motion. Friction is doing negative work. And however much negative work happens, that's how much mechanical energy decreases by. Okay? I want you to kind of just marinate in this for a little bit. Like let this soak in your, make connections here. Any questions? Points of confusion? Hey, is this a valid connection? Like I'm seeing this. Is this true always? Any questions? Okay, this last one just kind of demonstrating the same thing with numbers. Here we start with 100 joules of potential energy and we start at rest. As it slides down the ramp, we're decreasing potential energy but increasing kinetic energy. So the total mechanical energy is still 100. And as this goes down, because mechanical energy is still conserved because we're ignoring friction, we can figure out the remaining pieces of that. Tell your neighbor what those missing pieces are. We're going to say this is ground zero. Okay? Does that make sense? So 0 and 100. Good? Okay. I will upload a worksheet that we'll do on Monday, some point.